In episode 2, we watched something historic unfold. We saw Lee Sedol, a true human master of Go, outplayed by a machine. But it brings up a really fascinating question. How does a machine actually think? It's one thing to program a computer to follow rules, but how do you program intuition? Today, we are going to slow down and look inside the mind of AlphaGo. We'll explore how it actually makes decisions and how it managed to outsmart the best of us. Look at the game of Go, black and white stones placed on a wooden grid. It looks incredibly simple, yet this is widely considered the most complex board game in human history. To understand why, you have to look at the math. A standard 19 by 19 grid Go allows for so many potential moves and combinations, literally greater than the number of atoms in the observable universe. Engineers tackled games using a strategy called brute force. To win, a machine would simply look at the board, calculate every single possible future move to the end of the game, and execute the one move that guaranteed a victory. That strategy is exactly how this machine, IBM's Deep Blue, defeated world chess champion Garry Kasparov in 1997, relying on sheer computational horsepower. Finding the right move with brute force is like searching a massive mansion by opening every single door, but the mansion for Go is far too large. Even the world's most powerful supercomputers would run out of time trying to calculate every possibility. To play at high level, a machine needs to bypass the maze. Conquering Go was never a hardware problem. Adding more processing speed won't help. Engineers had to build a completely different kind of architecture, a system designed to process information the way a living mind does. The foundation of this architecture relies on what engineers call neural networks. This is what's inside AlphaGo's mind. First, policy network. When the system looks at the game, this network acts as its intuition. It instantly narrows down millions of choices to just the few most promising moves, ignoring the rest of the board without ever calculating the future. Once the board is narrowed down, the information moves to the value network. This network acts as AI judgment. It scans the patterns on the board to answer one immediate question based strictly on its exact arrangement of stones who is winning right now. By combining these two networks, the machine feeds the board state the way a human expert does, successfully eliminating the impossible task of calculating every single potential outcome on the board. But intuition alone doesn't place stones. Once the neural networks narrow down the options, a separate system steps in to plan the attack. This is called as the Monte Carlo research. Imagine you have 10 seconds to pick the best of 10,000 restaurants. You don't read every menu. You use your intuition to focus on a generally good neighborhood like the Italian district. In the expansion phase, once you are in the right neighborhood, you pick a specific pizza place to investigate. In the game, this represents the AI locking in on one specific move to explore. Next is the simulation. The AI takes a rapid test by playing out a simulated game from that move to the very end. It completes this entire scout sequence in a fraction of a second to see if the move results in a win or a loss. Finally, in the back propagation step, the AI updates its internal notebook with the result. It repeats this four-step cycle thousands of times, logging wins and losses before it ever places a stone on the actual board. AlphaGo does not care about maximizing its points margin or crushing its opponent. Its logic is aimed strictly at maximizing the probability of winning. In practice, if AlphaGo is presented with the move that wins by 20 points but carries a 80% chance of success, and a move that wins by only 1.5 points but carries 99% chance of success, it will choose the smaller, safer victory every time. By pairing a neural network sensory intuition with this rigorous probability-driven search algorithm, the machine deployed a hyper-efficient strategy that felt completely alien to human masters. That explains how the machine makes decisions. But there is a final piece to this architecture. How exactly did a string of code acquire intuition in the first place? The answer lies in the program's final iteration, AlphaGo Zero. Unlike previous versions trained on thousands of historical games played by human experts, AlphaGo operated on the principle of Tabula Rasa. It was born on a completely blank slate, fed absolutely zero human data. This diagram illustrates the training method called reinforcement learning. As shown in the top timeline, the system played millions of games against itself, starting with completely random moves and updating its neural networks based solely on wins and losses. AlphaGo compressed thousands of years of human trial and error into just 3 days. AlphaGo arrived at a set of highly effective original strategies that human experts simply hadn't seen before. This timeline tracks the machine's progress. Notice how the corner sequence evolved. At 10 hours of training, it tried weak moves. By 47 hours, it independently discovered human sequences. But by 72 hours, it invented its own superior variations. This architecture validates the potential of Tabula Rasa reinforcement learning. By achieving superhuman performance, the system demonstrated a method of cracking problems once considered decades out of reach. It serves as a proof of concept for a machine that creates its own expertise, providing a blueprint for tackling other complex domains where human data is missing or incomplete. Thank you for watching. Hope you enjoyed the video.